to thank the organizers, both from IIT Guwahati and Tokyo Tech for organizing this, and specifically Professor Banu Das for chairing this session and all the other chairs as well. So it's really a great pleasure for all of us to be involved in such a noble enterprise. And I hope we'll do justice to this collaboration. And it's really nice to know that a publication has already resulted from this collaboration. I hope many more will be forthcoming in the future. So my talk is about a new technique we have been developing for the last several years. Well, it was new last several years ago, but now it's not new. But it's new in the sense that we noticed that people are still somewhat hesitant to fully endorse what we are doing. And one of the purposes of this talk is to convince whoever is not convinced to take this idea seriously. This is especially important because one of the editors of PhysRev specifically told us that if you want to convince people, you should compare with DMRG. So I'll tell you what we are doing, and this talk is about the comparison of, so let me share, and it is basically, so are you able to see my slide? So can you see my PPT, please? Hello?
Yes, yes.
You can, okay. So as you can see, the title of this talk is a comparison of this new technique we have been developing called non-chiral bosonization, NCBT for short. N means NC is non-chiral, B is bosonizer, T is technique. Okay? So NCBT, that's what we have been calling it. And DMRG is, of course, density matrix renormalization group, which is a very powerful technique for studying interacting fermions in one dimension. Of course, we have started doing the DMRG simulations on our own using the existing open source software by the White's group in Irvine. It's called iTensor. But we are a little, we are a late entrant into this game, so we don't have that much of an expertise. So this comparison that I'm talking about is going to be a comparison with already published work in DMRG. So I'm not going to compare with our own simulation, which is still going on, but rather I'm going to compare with an existing paper on DMRG, which I'm going to describe. Okay, so my collaborators, my first collaborator in this particular topic was my former PhD student, Joy Prakash. He's now in SN Bose Institute in Calcutta as a postdoc. And my current PhD student is Nikhil Dani. So I tried to persuade him to work on this as well. And hopefully we'll be able to, convince the naysayers in due course if there are any. Okay, so see, the whole point is that, as you all know, or maybe many of you know, because this is an expert audience, see, the Bosonization is a technique which enables a very efficient analytical study of fermions in one dimension specifically, and where the interactions are as easy to handle as the free theory, because they tend to be quadratic in the, so basically Bosonization is a mapping that maps the original fermions into a certain kind of bosons, so that the theory of an interacting fermion is mapped to a theory of free bosons. So what happens is that if you have a theory where you have interacting fermions which are mutually interacting, but on top of that you also have impurities. So typically what happens is that the interacting Fermi theory is exactly solvable in this Bosonization language, provided the mutual interaction between fermions are confined to what's called forward scattering. That means that there is no sign change in the momentum transfer. So if two fermions scatter, they kind of move in the same direction as before. So the original fermion, so they don't change directions, but they change magnitude only. So that's called forward scattering. So if you only restrict your attention to forward scattering, then the model of interacting fermions in the homogeneous case is exactly solvable. But as you very well know, in the early 90s, there was a seminal paper by Kane, Charlie Kane, and Matthew Fisher, which started the subject of impurities in a Luttinger liquid. So the idea is that so what they did was that they the conventional approach which they advocated was that you take this bosonization framework, which is applicable to studying interacting fermions interacting with forward scattering interaction. You solve that exactly and use that as your starting point, and then you handle impurities as an afterthought. So you introduce impurities. So when you bosonize the system with impurities, what will happen is that in the conventional approach, the impurities will lead to a Hamiltonian which is non-local. So it leads to what's called a Sine-Gordon theory. So according to us, the main problem with this is that the impurities are thought of, they are introduced as an afterthought, that it's the interaction between fermions that treated very well, but the impurities themselves, which cause so much drastic change in the ground state of the system. I mean, if you take free fermion and put impurities, it just messes up the whole system. And yet, such systems are, those are not even perturbation, they're drastic changes to the ground state of the system. And yet they're, introduced as an afterthought almost. But then, so the conventional approach involves using RG on top of this Sine-Gordon extra term, and then you try and draw your conclusions that way. So what I thought of several years ago was that that is not acceptable, because impurities certainly should not be thought of as something that's an add-on. So that should be done first. So the interactions between fermions is a kind of a weak thing. Even though qualitatively it changes from a Fermi liquid to a Luttinger liquid, it is still some kind of a Gaussian deformation in some sense. So the way we did this was to modify the Fermi-Bose correspondence in the conventional bosonization. And let me see if I can bring my laser pointer. So this is the conventional bosonization, which maps the field operators to a certain collection of bosons here. So the non-chiral bosonization is basically an attempt to modify the Fermi-Bose correspondence by introducing this extra term, which doesn't spoil the Fermi statistics. So the fermions continue to anti-commute and so on because of this 2 pi and so on, 2 pi I. So that 2 pi I will not bring in funny signs there. So the funny signs is already contained here. The -1 comes from here. So those of you who know bosonization know what I'm talking about. So so the whole point is that this rho minus y is basically it encodes the backward scattering. So we assume that there's a cluster of impurities close to the origin, and you have fermions that are going to tunnel through, and some of them are going to scatter back. So the back scattering is captured by this modification here to the Fermi-Bose correspondence. So we have a paper in a mathematical physics journal where we show that this doesn't spoil any of the relations that are considered sacred. Okay, so I can give you a whole bunch of reference. So we have published close to 8 papers on this subject already, all except in PhysRev, and I'll tell you the reason why. So that's the reason why is exactly the reason for this talk. Basically, the editor said you have to compare with DMRG. Okay, so this is the new Fermi-Bose correspondence. You can also look at it, somewhere at the back on my board also. So this new is the right mover, +1 is right mover, this is left mover. So this lambda is 0 or 1, depending upon whether this modification is needed or not needed, and so on. Okay, so the idea is that this chiral bosonization is rigorously applicable for this system where you have this infinite number of negative energy states which are filled up to some level, whereas of course we study only a normal parabolic system where the states are filled up to Fermi level and we look at something close to the Fermi points. So in some sense, these two are qualitatively the same, but there are some subtle differences. So let's not actually go into that. So the point is that to cut a long story short, because I have spoken about this earlier in the last Tokyo Tech conference. So we were already in the last conference, I pointed out that we were successful in deriving this the most singular part of the density correlation function with interaction and with impurities in this really beautiful closed form. So this mod R is basically the bare reflection coefficient of the cluster of impurities near the origin, and VH is this Holon velocity. So I'm talking about spinless fermions here, and this is the slow part of the. So this is a very new result in the sense that we are the first one to explicitly derive a closed formula for this. So this is the most singular part. And of course, you may ask, like, how do you know this is the most singular part? That's we have explicitly proved this in a recent paper that was published in Physica Scripta in this year. I mean, it was already implicit in our earlier publications, but we felt it was necessary to make it explicit. So on not only density correlation, we can explicitly write down the entire full one particle Green's function. So you have different kinds of Green's function. When you have right mover, Green's function, and you have right, left, right, and so on. So and you see the various exponents here, gamma 1, P, Q, capital X, and so on. And this is with spin, by the way. That was the earlier one was without spin. So we have done both. So now I'll just point out what. So all these exponents are explicitly expressible in terms of the bare reflection coefficient of the cluster of impurities and this Holon velocity, which is in turn related to the forward scattering strength. So this is all already there in our earlier publication. So this is an explicit form for the Green's function. It's quite remarkable that you can actually write this down. So the claim is that this is the most singular part of the one particle Green's function, and the earlier slide was the most singular part of the slow portion of the density correlation. So now you can specialize to a case. So what happens is that you see, if you stare at these exponents, you'll see that they are not universal in the sense that they appear to depend upon the impurity strengths. So this is in contrast to what this conventional chiral bosonization suggests, that there is this famous cutting the chain and healing the chain. So that the claim is that if you have fermions which are mutually repelling, then an arbitrarily weak impurity gets amplified in such a way that the low energy physics is dominated by a scenario where that impurity is effectively infinite in strength. So basically, they claim that the exponents, there's only a binary thing. It's either the exponent is either infinitely strong or not there at all. So if the fermions attract each other, it's as if the impurity effectively disappears. So the fermions ignore the impurity and move about as if. So that's the conventional chiral bosonization approach. Now later on, I'll tell you the reasons why we feel that this is not very valid. Not only we are saying that there's a very influential paper by a group which has done DMRG with whom we have compared, also thinks that's not really believable. However, the vast majority in the community continue to believe that, which is why we are having trouble convincing them. Okay, so the idea is that there is a reason why the impurities or rather the exponents appear to be independent of the impurities, and that is that you see it is only the most general form of these correlation functions that have these funny exponents which depend on the impurities. However, if you try to look at any simplified version of this general correlation function, which is typically accessible through either exact solutions or numerical approaches, which typically involves, say, equal time correlation functions and so on, then all of a sudden you'll see that the impurities, the impurities in the exponents, they cancel out miraculously, and you end up. So our formulas exactly say this, that if you look at say spinless fermions for say right movers and right movers, where x1 and x2 are on the same side of the origin, so on one side of the impurity, then you'll see that lo and behold, the correlation functions actually have an exponent, so they go as position to the power p plus q, and neither does p nor q depend on the impurity strength. Okay, so that's the whole point. So that this even here, so it doesn't depend on how you do this. So regardless of whether you do it as x1 times 2x1 or x1 plus epsilon, whatever it is you do, the impurity cancels out. So same with the right left correlation function. Of course, this is identically zero in a homogeneous system, but then it's not zero when you have backward scattering from the impurities. And then you see that explicit formula also, that oddly enough, the impurity strength cancels out, because we are looking at equal time correlation functions where x1 and x2 are in some sense proportional. So this is probably the reason why it's hard to pick up this impurity dependence of the exponents, because many exponents, the impurity kind of surreptitiously cancels out. And then it's only in the most general form of the Green's function the impurity survives in the exponent. So I'll tell you, there is a, okay, let me get to that. Noting. Okay, so what is the main advantage of using NCVT? So basically it includes the presence of impurity right from the start. So that means the free theory plus impurity is exactly solvable, using trivial undergraduate quantum mechanics. But therefore, any method worth its salt should also be able to treat that system equally easily. Unfortunately, conventional bosonization cannot even handle free fermions plus impurities easily. That becomes a Sine-Gordon theory in the conventional approach, and that's not acceptable according to me. So our approach treats free fermions plus impurity as trivially as you would, an undergraduate quantum mechanics student would easily solve that as well. Okay, so we are not going to introduce impurities as an afterthought. It's encoded into the Fermi-Bose correspondence. So, so the whole idea is that we want to see if we can compare the results of NCVT, which we have rigorously proved analytically that they're absolutely correct. And so we want to see if we can compare with DMRG. So to do this, we have to, well, all the existing code deal with lattice systems. So we start with a continuum system, kind of, it's the reverse of what we normally do. We start with a lattice system and then map it to a continuum to do analytical work. But then here we started with, this is the analytical model that we have used to study with, to do NCVT with. So the non-parallel bosonization studies this. So you have this right movers kinetic energy here, and this is the impurity. So this is the backward scattering, the right becomes the left because of this. And then this is the conventional forward scattering. So there's right plus left. So there's a conventional forward scattering between fermions, and this is the, when fermions bounce off the impurities, this is what you get. This is the impurity Hamiltonian. This is the conventional kinetic energy. So the idea is that you want to sort of latticify the system. So go from the continuum to the lattice. So you make this approximation that k is sine ki by a, where a is very small, and then you can convert this to a lattice system. And this is what we look. So instead of R, we can think of it as up, because the chords typically deal with fermions with spin, but single species. So here, a right mover and a left mover is like up spin and down spin. So instead of two species like right left, we have one species but with spin. I mean, it's just terminology. So we kind of identify up as R and down as L, and then you get this, and then this you can directly dump onto your DMRG code and see what you get. So that's what we are running now. But then, the computational resources required to extract Luttinger liquid physics from DMRG is considerable. And if you read the literature, you'll see that it's a very non-trivial task indeed. So, so instead of, we are going to do it ourselves, but then since we don't have our own results, we are now forced to compare with already existing work. And one of the important works in this field is this DMRG studies of impurities in Luttinger liquid. This is the title of this paper, which was published in Progress of Theoretical Physics many years ago. And they use DMRG and their own favorite approach they call functional renormalization group. And what they conclude is that the universal physics predicted by Kane and Fisher that only sets in at extremely long and experimentally irrelevant length scales. So, so this is an important point they make, that they are actually not able to reproduce the universal physics produced by conventional bosonization. So, so you can see in this plot. So, okay, I'll get to that plot later. So the other notable work.
Excuse me. Yeah, you've got 5 minutes.
Okay, I'm done. This is
okay. Fine. Yeah.
Okay. So, so there's this other approach. This other work which we haven't compared with, but it's notable as well because they use the infinite DMRG for studying continuum systems directly without doing the lattice thing. So, whereas the you see, the non-chiral bosonization gives you so now what we're going to compare. So this paper, the paper by Scholwok et al., they actually do a DMRG for the density of states exponent near the impurity or at the impurity. So of course, our non-chiral bosonization gives you an explicit formula for this exponent in terms of the the Luttinger parameter, the homogeneous Luttinger parameter K rho, and the Baer's impurity reflection parameters. So, so now you can see, of course, for the half line. So if mod R is 1, which is the perfect, infinitely strong impurity, that agrees exactly with Kane and Fisher. So there's a reason why a non-chiral bosonization is going to agree exactly with Kane and Fisher when the impurity is either infinitely weak or infinitely strong. We have rigorously proved this as well in our several papers. So, however, in between we differ, and so now the question is, how do we compare with DMRG is the question. So now, if you stare at this plot, so these solid diamonds and triangles and squares are the DMRG simulations. So you can see that the solid circle corresponds to the impurity strength being 1. So this in some units, and the solid square is impurity strength 2, and the solid diamonds is, so this is the DMRG by Scholwok et al. So so this solid diamond is 4, and then the solid triangles is half line, that is infinitely strong impurities. So now these horizontal solid lines is NCBT. The horizontal solid lines are non-chiral bosonization. Of course, the x-axis is the number of sites. So we have, I mean, our theory is for the thermodynamic limit where n is infinity. So strictly speaking, we should look at, n very large. But then you can see already that the solid shapes are always hovering close to our lines. See, whereas if you believe the Kane and Fisher result, they should all converge to this b equal to infinity result. So this thing, of course, this seems to go up, but then you see this actually comes down and touches our line exactly. It doesn't seem to be going up at all. So it's like coming down the, see, what is diamond? Diamond is 4. So diamond is actually coming and touching our horizontal line, which is the non-chiral Bosonization result. So same here also. So the thing is that, of course, you can say it's still inconclusive because we have to really extend this beyond this. See, what I find suspicious is that this paper kind of stops here when it comes to DMRG. The ones which are not filled in, they are their other approach, which is called functional Bosonization. So which is not really numerical; it's more sort of analytical. So point I'm trying to make is that I feel that there is, by staring at this, there is a case to be made that the impurities are in fact not universal, and it's also consistent with the remarks they have made in this paper as well, that the universal physics really sets in at experimentally irrelevant length scales. And I feel that they're saying that because they don't want to antagonize the community. Deep down inside, they probably don't believe that there is anything universal. And we certainly don't believe. And we have rigorously proved this in our various papers. Okay, so I'm going to wrap up. So the idea is that we feel that by staring at these plots already, that the non-chiral Bosonization results show that the exponents are in fact not universal. They depend upon the impurity strength, and this is consistent with the work of Schobach on DMRG, and the analytical papers, we have published 8 of them. The most recent one is this, which explicitly does a perturbation theory using conventional conventional fermion perturbation theory, and compares term by term with the corresponding expression. So you take the non-chiral Bosonization closed form result and expand that in terms of the fermion coupling. And term by term, we compare with conventional perturbation theory, there's Feynman diagrams, and each term matches term by term. So in fact, up to second order we have done. Second order is enormously complicated, the expression, and yet every term matches. So the second order term is so complicated, it's remarkable that it matches so well. So we feel that there's absolutely no reason to disbelieve NCBT, non-chiral Bosonization, except that editor of PhysRev feels that this is not good enough. You have to do DMRG. We have done that as well. So I hope if they are listening, I'm sure they're not, but if they're listening, they should take it seriously. So I thank you for your patience, and I'm open for questions.
Okay, so thank you very much, Professor Settler, for a very nice talk. And now we can have some questions from the audience or comments. Yes, we have time for questions. So please go ahead if you have any questions.
Yeah, I was going to share this. So this is the paper that we wrote recently. So it was the Physica Scripta thing. Mm-hmm. So you can see here that we have in the appendix, we have explicitly shown by comparing term by term. So if you take this density-density correlation, you do this conventional fermion perturbation theory up to second order. So you can see the second order term is so enormously complicated here. So this is what it is. And so yet, can you see this paper that I'm able to see?
Yes.
Okay. Yeah. So this. So if you take your the non-chiral bosonization result, expand up to second order in this fermion coupling, what you're going to get is this expression, and this is also the same expression you get if you do conventional fermion perturbation theory using Feynman diagrams. So it's really remarkable, and this is the reason why this deserves to be taken seriously. We are in our earlier paper, we showed the same thing for Green's function. In fact, we did even better. We showed that the Green's single particle Green's function obeys the exact Schwinger-Dyson equation without, I mean, not perturbatively, exactly. So it's provided you, chop off the less singular parts. So there is a precise sense in which our results are capture the most singular part of the, we have explained that. I don't have time to go into that. So you take the Schwinger-Dyson equation and chop off the less singular parts, and the Green's function obeys the, the truncated Schwinger-Dyson equation, which only takes into account the most singular parts. So so I feel this deserves to be taken seriously. So I'm open to questions. If there are no questions, I thank all of you for listening and for participating in this conference. And thank Professor Das for chairing the session.
Okay, thank you, Professor Settler, for a very illuminating talk. I think, I'm sure the audience would have benefited in many ways. Okay. So that brings us to the end of the third session, which was the final session of today. So maybe I'll sort of hand it over now to Professor Ghosh or Professor Kuze for any comments.
Yeah, thanks everybody for very nice talks and basically keeping the time. It really went, the first day really went in a very well-organized way, and we didn't have any technical glitches. That was one of the concerns, certainly. So thank you all. And I think the participation was quite handsome. I could see there are several students attending. And so thank you, everybody. So Professor Kuze, if you want to add something, you may please add.
Yeah, I agree. Yeah, it went very smoothly, and the time was kept thanks to the chairs. So yeah, we see in the second day, which is Thursday, not tomorrow. Yeah, the same time.
Yes. So that will be 9 o'clock Indian time and 12:30 Japanese time.
Yes. Yes.
Okay.
So
thank you very much.
Thank you very much.
Nice day.
So I will stop recording.